Hey there. So we are doing a two-part series. The first one started on Thursday, and then the second part to this is on Tuesday. And we're building, so please make sure that if you haven't gone through the blank worksheet that you can print off, you can print it off from the website and filled it in and just have a sense for it. And make sure you do that before Tuesday because I don't want people to be lost. Also, remember we always have these links at the top. Some of these are really long. This is a pretty favorite topic across the internet in chemistry. You can find tons of links. If the way I'm explaining it doesn't work for you, totally can find tons of others. So don't let yourself stay confused. Go look for those answers. So we started today just kind of reviewing about the difference between ionic and covalent yet again. And I know it's probably sounding like a broken record, but with the ionics, that's just the idea that you've got something that has an electron and it's giving it to someone else who's in turn giving them energy, basically. So the chlorine has extra energy, and so he's giving his energy to the hydrogen so that the hydrogen will release and give, basically I guess it's this one, to chlorine. And when that happens, then chlorine is no longer neutral. He has a negative charge because electrons are negative. More electrons means negative. And then hydrogen has a positive charge because he's missing his electron. So that's in contrast to this picture over here where we have hydrogen and he's got his electron and he's donating to the shared situation. And then we have chlorine with his electron who's also donating to a shared situation. When they share, we use a line. When they don't share, we use like brackets and charges. So it's a very big difference in how they look. This is a very rare and unique molecule right here. And it's a good one. It can be described as ionic or covalent, but most of the time you can't say that for most things. But it's a good one for an example. Remember that also ionic things, are on the left side of the periodic chart. Remember you got your periodic chart. So the ionic things are something that's on the left side with something that's on the right side bonding. Remember these guys on the left want to go positive and then the right side wants to go negative. That's ionic. Remember that if you're going to be covalent, then you're sharing electrons, you're not transferring. And the only guys that have enough electrons to do the sharing are the ones over here. And hydrogen is weird, so he can do some ionic-y kind of stuff. So he's weird. So hydrogen's in there too. Remember, hydrogen can float all over. So it'd have to be like 2 things in here, or 3 things, or 4 things in this section, or with hydrogen that are doing covalent. So most of the rest of the time we're going to be talking about covalent. We have one more last example. So we've got our chlorine right here and our MgCl2. So the chlorine, these are both nonmetals, and that's how we know that it's covalent. And draw them each with 7. And you can see we've got the one electron, and they're going together to make a bond. Don't overly think about who's doing what with the bond. This picture, it kind of makes sense, and you can kind of imagine there being an electron from him and him. But that's not how we draw the structures, and it's a little misleading. So try not to worry about who's donating which electron, because sometimes they can do things unexpectedly. And then we have MgCl2, and our Mg in this case is giving an electron to the chlorine and then to the other chlorine. And these would probably line up like this because we've got a positive 2 in the middle and then the negatives. You can also see it where they will write this and then they'll put a 2. That's okay. The left picture is really nice because it shows you that lattice structure we talked about before, where you end up like with this cubic shape with all of these atoms like all lined up, on it. Kind of shows that a little bit with the alternating here. Okay, that's the end of the ionic stuff. So covalent, we're going to look at things that are more than just 2 atoms. The 2 examples we had just 2 atoms. And of course the only way that you can attach 2 atoms is with a straight line. We're going to have a lot of option coming up though. So covalent molecules are ones that have, again, they're over here on the right side of the chart. You'll see this is where we are. And on the left side you got your hydrogen. And I kind of in class went into this big spiel about the shapes of the molecules. And basically the idea is that everything in our body, a lot of things in the world, these are all big molecules made up of little molecules. The shape of the little molecules matter because they keep their shape even when they become big molecules. So something that might have that shape, if you build something with a lot of this kind of shape, it's going to look something like something. And the way that things look, so I talked about how, like, if you had a whole lot of things joined together and they had like a Pac-Man kind of a shape, like this kind of, this space could be the perfect size for like holding onto a cancer molecule, or it could be the perfect size for transporting something throughout the body. So the overall big structure is a result of all these little tiny molecules in here being bonded in a certain way. So that's why we care about it. Then we have the octet rule, and that's that molecules or polyatomic ions tend to form structures where there are 8 electrons. Also note, this is kind of funny, the octet rule completely always applies to this section right here. So we've got a great big periodic chart, and it's only those guys that are always 8. So 8, 8, 8, 8. Those guys, you got to get them to 8. So I know you're like, we have a great big periodic chart. Why do we care? Well, these are the ones that make up our bodies. These are the ones that make up our pharmaceuticals. Super important. So these are the ones that are going to be in most of the chemicals and the compounds that we have you draw structures for. Now, if you are below this line, all of these guys, you still can do covalent bonding, and you're going to aim for 8, but you can do more. And then we have a few that just can't quite do 8. You're going to go left. So boron. So sometimes boron can fit 8, sometimes. But you would be told in that situation, you're going to assume that he can only hold 6. You're going to assume that beryllium can only hold 4 and that hydrogen can only hold 2. And I know you're thinking, wait, beryllium is ionic. I know. He's weird. He can do sometimes some covalent things. We're going to show a picture of him. We know that experimentally. That's how we know it. So I think I've covered all the exceptions. It feels like a lot, but you'll get used to them. All right, so there's kind of a series of rules. If you follow them in order and you get used to the process, you're going to do a great job. But you do have to kind of get used to the process. So first of all, what you want to do is add up the total valence number of electrons. Now, we did do a review in class reminding everyone, this is the green numbers. The first column has 1 valence. The second column has 2. Third has 3, 4, 5, 6, 7, and 8. So if it's in this column, then it's going to have 3. Or if it's in this column, he's going to have 6. So keep that in mind. So those are the valence. We're going to add them up. If it has a charge, you would add more in if it's negative and take some out if it's positive. And that number of electrons is going to come from your total count. So you're going to count everything, and then if you have a charge, you'll either add in or remove some. You want to put a big old box around it because that is the real number of electrons. All right, so we're doing an example with CF4. So C has 4 valence electrons, F has 7, but there are 4 of them. So that's 28. So 28 plus 4 is 32 with our great big box. Step 2. Write down at least the least electronegative element as the center. So if you can't remember, so this is right where, whoops, this guy right here, he's the most electronegative. So you want to be away from him. Carbon's like over here, so no, he's over here. So you can see how he's far away from that fluorine. Fluorine's the most electronegative. Also, it's almost always the first element. So question, why can't hydrogen ever be the center? If you look back up, hydrogen right here, he's right here, he can only hold 2 total electrons. He's really tiny. He can't fit more. He can contribute 1 and have a total of 2. He can't fit 8 around him. He can't fit any more than 2, which means just 1 bond. So if you can only make 1 bond, you can't be the center of anyone. You have to be on the outside. Oops, and I think I meant that to go there. Third step. You're going to write the other elements around it symmetrically and evenly spaced. So we've got our fluorine, 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 and fluorine. So see how they're kind of evenly spaced? And then you're going to draw lines from the center element to the ones to represent bonds. So bond, 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 bond. Remember that each bond contains 2 electrons. That's why I've got little 2's around it. Now this is a step that is so easily missed right here, this 5th step. Make sure that central element has 8, and if not, you're going to add pairs of electrons. It's kind of unusual to have single electrons. You would be adding pairs of electrons, and you may end up removing them later. All right, and then make sure that all the outer elements have 8 by adding an electron pair. So you can see I've added in all the dots in all those cases. And then on step 7, count the number of electrons in the structure and compare it to the real number. So I've got them highlighted here, but 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. And I'm telling you, it is really easy to count by 2s and then to make a mistake. But that one definitely had 32 pairs of electrons, or 32 electrons, 16 pairs. Now, I've got 2 stars here. This is going to be for next time. If you have too many real electrons, meaning that like your count doesn't match with your too many, this like that would be like if your count had turned out to be 30. See how 30 is less than 32, so you have too many real electrons. You would place extra electrons in lone pairs around the central atom. If you have too few, you're gonna make double bonds, and each double bond you make, it will remove 2 electrons from the total count. Again, that's gonna be next time. And again, can you make a double bond to hydrogen? No, you can't, because he can only hold 2 electrons, which would be 1 bond. You can have odd numbers of electrons, but it's very, very unusual. And they act really crazy, and they try not to be odd. And last but not least, you're going to make the most electronegative element. If it is an odd number of electrons, you're going to make it have a full octet first, and then you'll check your formal charges. All right, so then name your geometry. There's 2 ways you can name things. The electron pair deals with the electron regions. And the Vesper, it describes the location of the atoms, not the electrons. Don't forget we have these learning objectives, and this will be next time. But we're building on this, so make sure you have this. And I'm going to pull up the supplemental, whoops. And it is at the top. Here we go. All right, so here's our supplemental. And we did the first page. If you want to go ahead and do the next page, that's totally fine. His first left column right here, this is your total valence electrons. So hydrogen has 1 times there's 2 of them, that's 2. Beryllium has 2, and then chlorine has 7 times 2 is 14. When you add 2 and 14 together, you get 16. Beryllium has 3 valence, and then chlorine has 7 times 3 is 21, which gives you your 24. Carbon has 4 valence. 7 times 4 is 28, so your total is 32. Nitrogen has 5 valence. Chlorine has 7 times 3, which is 21, so together it makes 26. And last but not least, oxygen has 6. Hydrogen has 1 times there's 2 of them, 2 valence, which gives you 8. So that's our total electron count going on right there. Then we have our Lewis dot structures. So you want to kind of follow the order. The first thing you're supposed to do is write down the central element. In this case, notice you can't have a central when you only have 2. So that's fine. Just stick them both down there. The next thing you want to do is draw a bond. So there's your bond. It says give all the outer atoms enough 8 electrons. But remember, hydrogen can only have 2. So they're all good. And you'll notice that our total count of the electrons is 2. Now on our next one right here, you start and you're going to put beryllium in the middle. He's the least electronegative. And then you're going to draw your lines. And then you're going to put your outer electrons in. And if you count those up, 2, 4, 6, 8, 10, 12, 14, 16, you get 16. Notice right now everything is matching. So we're great. 2 and 2, 16, 16. This page is designed that way. We will have some differences. And then we have boron. Draw the lines to the chlorines. Fill in the chlorines. So 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22. Wait, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. I'm going to count that one more time because I have too many things in there. This is what I'm talking about. It's really easy to miscount something. Okay, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. There you go. We're continuing this on. Carbon's in the center. Bromine is all on the outside. You draw your bonds. And then you fill them in on the outside with all their electrons. When you add all of those up, you're going to get 32. Now, nitrogen is our center. We put our chlorines on the outside and we draw our bonds. And then there's a step that we haven't really had to do so far because everything's been covered. But if you count up nitrogen, if you don't put that lone pair in, he's only got 6 electrons. You've got to give him the lone pair. Then give all the outer chlorine atoms their electrons. And that puts you at 26. And last but not least, your oxygen here. He had his bonds to hydrogen. That's 2. And then you need to fill them in with 2 pairs of electrons, and that'll give you your 8. Now, as for these names, we actually had little pictures in class. I recommend clicking on, there's this molecule viewer. You probably should do that to make sure that you get the idea of these pictures. The electron geometry and the molecular geometry, so they're going to be the same. This will be the same as the electron geometry until you have lone pairs, and that's on the central atom. So if you look right here, this shape, it looks linear, like it's a line, linear. It has to be linear. And same thing, like if you have a middle atom and you're trying to get these guys as far apart as possible, it's linear. Now this next shape, what happens, I should include this as linear in both of those cases, but this next shape, what happens is you've got something in the middle and it's coming out like this. That's how this BCl looks. It's flat. If you were to pick it up and look at it from the side, it would look completely flat and in a plane. And the plane has a triangle shape to it. So triangle, trigonal, that's why we have it like that. And then it's all in one plane. It's hard for people to see these without the models, but I'll have the models out next time also so that you can look at them. Then the next one is tetrahedral. The reason we call this tetrahedral, and this is especially hard to see, so without models your first time. So imagine that these are both in the board, and I'm going to draw this. Imagine this thing that I'm drawing is coming out at you. And then imagine that this is going behind your screen. It's a 3-dimensional shape. And it's called tetrahedral because it has 4 faces. So like this is one face, and it's got a face on the bottom. It has a face on the back right hand side, and it has a face on the back left hand side. Again, so much easier to see with models, but I have a molecular viewer saved in our notes. And again, no lone pair, so tetrahedral. By the notes, it's near the notes. And then the next 2, we still call them tetrahedral because it's considered, and this is not the best description once you can start having lone pairs, but that you have 1, 2, 3, 4 regions. Even though bonding electrons are completely different from lone pairs, we call them regions. So in this one, and this one, our central atom has 4 electron regions. And so all of them are called tetrahedral, but you could imagine that those are not good names for them. So for the next one down, trigonal, I just realized I put planar, and this should totally be pyramidal. So for the trigonal pyramidal, I did it correctly on the other one. It's like you've got an atom, and you're going to imagine like there being a little pyramid behind it, like it's making this little pyramid kind of a shape. That is what he is. And last but not least, bent. A bent guy. He just looks like this. It just looks like a bent line. It's all on one page, and it's all happy and good. I'm going to finish these last little sections off. I just want to make sure that I touch on this one and this one. And then we'll call that good. So phosphorus has got 5 electrons. Chlorine has got 7 times 5, which is 35. So our total is 40. And then sulfur has 6. Fluorine has 7 times 6. So our total is 36. All right, so phosphorus, here we go. Phosphorus, 1. Well, here, wait, I'm going to put them all around him. I can't do it without the lines. I just have to put those lines in. So notice that makes 2, 4, 6, 8, 10. 10 around that phosphorus. That's just the way it is. He, in this case, has to go more, and he's allowed to because he's lower on that periodic chart. tell you, if you go back and you count all these up, you're going to get 40. And then over here with the SF6, you put the S in the middle. F, 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 F. And again, same situation. If they're all attached, then you're just going to make that sulfur be bigger and hold those extra electrons. And then we've got all these things in here. I realized this is 42, so 42 plus 6 is actually 48, not 36. And if you go back and you count all these, you are definitely going to get 48. So this guy's name right here, it's Trigonal Pyramidal. And this guy right here is octahedral. And they also had the same, because they don't have any lone pairs on the middle, they have the same molecular name. All right, that should take care of it.